This is number 61 on Chapter 4. An enemy ship is on the east side of a mountainous island as shown in figure P4.61. The enemy ship has maneuvered to within 2,500 meters of the 1,800 meter high mountain peak and can shoot projectiles with an initial speed of 250 meters per second. If the western shoreline is horizontally 300 meters from the peak, what are the distances from the western shore at which a ship can be safe from the bombardment of an enemy ship? So, first of all, this diagram looks a little different from the one in the book because they flipped west and east, and that got really confusing. So, this is just a diagram of what's happening. So the enemy is here on the east side of the mountain peak, and they shoot missiles over the mountain that's 1,800 meters high. And we're here on this side, and there's a western shore that's like 300 meters from the peak. And so we want to know where we can be safe. So because they don't give us the angle at which the projectiles are launched, we want to find the maximum and minimum values of theta where the missiles can go over the mountain, and then find out their horizontal distance to see where we'll be safe. So it'll be either like here before the missiles hit or here out of range of the missiles completely. So that's just the scenario of the problem. So first, we want to use some kinematics. So the ones that we're going to use are y equals velocity y initial t plus 1/2 gt squared, and x equals vx initial t because there is no acceleration in the x direction. So here, using this equation, we can get t in terms of x and v. So we get t equals x over v cosine theta because the velocity in the x direction is the velocity at which the projectile is launched, cosine theta, the angle at which it is launched. So we take this equation and we plug it in to the first one. So we get y equals v sine theta times x over v cosine theta plus 1/2 g times x over v cosine theta quantity squared. And then we can simplify this, so we get y equals x tan theta plus gx squared over 2v squared cosine squared theta. So now it seems like we're kind of stuck because we don't know what theta is. But using the identity sine squared theta plus cosine squared theta equals 1, if we divide both sides by cosine theta, we'll get tan squared theta plus 1 equals 1 over cosine squared theta. So we can plug this so we have 1 over cosine squared theta, which we can plug into there. So I'll shrink this. So if we plug that in, we'll get y equals x tan theta plus gx squared over 2v squared times tan squared theta plus 1 Then we get y equals x tan theta plus g x squared over 2v squared tan squared theta plus gx squared over 2v squared. So this is a quadratic equation where we can find tan theta. So if we plug in the values we know, and then we'll move y over to this side so it can equal 0, we'll get negative 9.8 meters per second squared times 2,500 meters squared. And x is 2,500 meters because we want to find, because like that's the, when x is 2,500 meters and y is 1,800 meters, that's like the only point where we have both the x and the y values available. So we just use that coordinate to find what tan theta is. So negative 9.8 meters per second squared times 2,500 meters squared over 2 times 250 meters per second squared tan squared theta plus 2,500 meters tan theta plus negative 9.8 meters per second squared times 2,500 meters squared over 2 times 250 meters per second squared minus 1,800 meters equals 0. So like this is kind of, it's like this second line here, like moved around, but it's still the same equation. So if we solve that equation, we will get tan theta equals 1.197 or tan theta equals 3.905. So theta equals 50.11 degrees, or theta equals 75.65 or 64. So what we know from this is that the minimum angle at which the projectiles can be launched is 50 degrees in order for the projectiles to make it over the 1,800 meter high peak. And the highest theta that works is 75.64 degrees. So since we have the thetas, we can go back, and since we want to find the total range in the x direction that we can have from these theta, we'll have to use kinematics plugging these values in. So we know that we want to use the equation x equals bx initial t to find the horizontal range, but we don't have t. So to find t, we have to use the kinematics in the y direction. So we can use the kinematic vy final equals vy initial plus gt. Because if we can find time at the highest point, then we can just multiply that time by 2 to find the amount of time that the projectile is in the air before it hits the ground. So we know that at the highest point, the velocity in the y direction will be 0. So t equals negative v sine theta over g. And we have two values for theta. So we can say that t1 equals negative 250 meters per second sine 50.11 divided by negative 9.8 meters per second squared. So the amount of time that it takes for the projectile to reach its maximum height if launched at 50 degrees will be 19.58 seconds. And then if we do the same thing for T2, where we plug in 75.64 degrees for sine theta, then we'll get 24.71 seconds. So now that we have the amount of time that the projectile is in the air for it to get to its maximum height, we multiply each of those times by 2 to get the total amount of time that they're in the air before hitting the ground. So we have x equals 250 meters per second cosine 50.11 times 2 times 19.58 seconds. So this is the horizontal range when the projectile is fired from the minimum launch angle of 50 degrees. So this will equal 6,276 meters. So that's that. And then so for x2, when the launch angle is at its maximum of 75.64, we'll get, so we plug in 75.64 times 2 times 24.71 seconds, because that was the amount of time that it took for the projectile to get to its highest point when launched from the maximum angle of 75.64 degrees. And then for that, we'll get 3,065 meters. But the question asks the distances from the western shore. So we have to subtract 2,800 meters from each of these values, because this x range just tells us how far from the initial point. So if this is like the enemy ship and that's the mountain, it tells us the total distance from the ship to its landing point. But what we want to know is this distance. When we subtract the shore, which is 300 meters, and subtract how far away the enemy is from the peak, which is 2,500 meters. So we do 6,276 meters minus 2,800 meters, and that equals 3,476 meters, and 3,065 meters minus 2,800 meters, and that equals 265 meters. So so we know that, okay, so ship, mountain, so there's these two distances. So this distance is the 265 meters, and this distance is the 3,776 meters. So we know that you'll be safe if you are closer to the shore than 265 meters, or farther than 3,776 meters from the western shore. And that is number 61.